So let's begin the chapter 5 molecular model exercise discussion. We're gonna be using the molecular model kit to talk about some key topics in chapter 5. The first topic to bring up is this idea of enantiomers. Enantiomers represent non-superimposable mirror images. So to show you these two enantiomers, I've gone ahead and made a model of each of these two compounds. So in this case, we have these two compounds. As we can see in one of the compounds, the fluorine is wedged, the hydrogen is dashed in the back. In the second compound, the fluorine is wedged, the hydrogen's in the back. However, the position of the chlorine in one compound, it's on the left, in the other compound, it's on the right. These two compounds represent enantiomers, non-superimposable mirror images. As we can see, although they look like mirror images of one another, if you try to overlay or superimpose these two compounds, what we see is that they do not perfectly superimpose. Enantiomers are non-superimposable mirror images, and you can prove that with a model kit. Let's look at this next case in terms of achiral molecules. So thinking about achiral molecules and axes of symmetry. To adjust the view slightly to give us a little more space. Okay, so when talking a little bit about achiral molecules are superimposable with their mirror image. So let's make a model of these two compounds and let's demonstrate that principle. Okay. So here is a model. So in the first case, the chlorine is wedged. In the second case, the chlorine is wedged and the bromine is dashed. These two compounds are identical. This molecule contains a clear plane of symmetry, splitting the molecule in half. As you can see, each side of the plane of symmetry is identical. We can also prove this by virtue of the fact that these two molecules are the same molecule. This molecule is achiral because it's superimposable with its mirror image. Here's the mirror image, and as you can see, if we rotate, we can superimpose and perfectly get the same molecule. If a molecule is superimposable, if it's identical to its mirror image, what that tells us is that this center is not a chiral center and this molecule is achiral. So achiral molecules contain a plane of symmetry, and achiral molecules are superimposable identical to its mirror image. Here's the compound in its mirror image. Here, after rotation, we see the compound and its mirror image are identical. These two molecules are the same, which tells us that this molecule is achiral. Okay. Let's bring up another topic. Meso compounds are pretty interesting in that meso compounds contain a chiral center, but they also contain a clear axis or plane of symmetry. Meso compounds are achiral. So let's demonstrate that. The key way that we can show that meso compounds are achiral is the fact that meso compounds are in fact superimposable with their mirror image. So let's take a few moments. Let's put together a model for this compound and then we'll discuss momentarily. So take a few moments, put together a model of this compound and its supposed mirror image using your model kit, and then we will discuss. So it may take a few moments to put together a reasonable model, but don't worry. I find that the proof and the demonstration that meso compounds are superimposable with their mirror image is best done with a model kit. And if when making a meso compound, you're suddenly wondering if you actually just made the same compound twice, that's not an uncommon experience or phenomena because, as we've discussed, meso compounds are identical to their mirror image. So if we're making a model of this structure, this compound and its mirror image, you're bound to run into some issues where you may end up making just the same compound. Okay, so let's set this up now. So here the alcohols are wedged, pointing towards us. Here the alcohols are wedged, pointing towards us. This compound is meso. It contains chiral centers, but it also has a clear axis or plane of symmetry. If we take the molecule and cut it in half, we see each side of the axis or plane of symmetry is identical. So as we can see, if we divide it in half, the substituents on the left are exactly the same as the substituents on the right. We can also prove this by taking a look at this compound and its mirror image. So here's the compound and its mirror image, its supposed enantiomer. As we can see, via rotation, we can show that this compound and its mirror image are identical. And thus, our original compound is meso. It contains a clear plane of symmetry. And if we take a look at its mirror image, it's identical to its mirror image. Thus, this compound is meso. So we've shown and demonstrated sufficiently that this compound is meso, and thus it's an achiral compound. Meso compounds are achiral compounds that contain chiral centers. Okay. Let's now talk a little bit about a guide for molecular rotation. So swapping any two substituents on a chiral center inverts the configuration. So if we start with an R stereocenter and we swap bromine and hydrogen, we end up with an S stereocenter. Now, if we swap two substituents and then swap two substituents again, you'll get the same configuration, but a different view of the molecule. Let's prove that with a model kit. So let's make a model of this compound, and let's show that swapping substituents successively is identical to rotation. I mean, whenever you're taught a rule or an idea, it's important to justify it to yourself that that rule or idea actually works, that actually has merit. So let's test that. Okay. So here is our model kit. So here the chlorine is pointing towards us, the hydrogen's pointing away from us. Here's the bromine, here's the alcohol. Now, if I want to rotate it so that the bromine's in front, I can do just that. Now we have the bromine wedged, the alcohol is pointing up, the chlorine is pointing to the right, and the hydrogen's in the back. So as we can see, we've converted between these two depictions via rotation. We can also convert between these two depictions via manually rearranging our bonds. Don't worry, I have another atom for that bromine. So if I swap my bromine and alcohol, that gives me this compound, which has the opposite configuration. If I swap my atoms once again, I've in turn achieved the same result that we achieved via rotation. Just to prove that, here is the original result. So as you can see, if you swap two bonds and then swap two bonds again, that achieves the same result as rotation of your molecule. Let's talk a little bit about how we can rotate bonds in our molecule. So in one case, any bond can be rotated 120 degrees, rotating all substituents 120 degrees. So for example, if we have the alcohol, chlorine, and bromine atom, we can rotate our bond and rotate our substituents 120 degrees, giving us a new rotated view. Let's show that with our model kit. So here's our initial view. I'm going to rotate my substituents 120 degrees. That gives me the bromine up top, alcohol to the right, and chlorine on the left. Again, here is our starting point. Here is post-rotation. Let's take a look at another example. This time we have an amine, an alcohol, and a methyl group. Let's make a model of this compound. And let's rotate our carbon-carbon bond 120 degrees. So here's our original structure. We rotated 120 degrees. Now the alcohol's up top, the amines on the right, the methyls on the left. Again, just to showcase, here's the original molecule. Rotation 120 degrees gives us the following view. This bond rotation was previously done on Newman projections, where we took our carbon-carbon bond and rotated our carbon-carbon bond 120 degrees, which in turn rotates our substituents. In fact, this view is almost Newman-like in terms of how we're looking down. This time, instead of a carbon-carbon bond, this carbon-hydrogen bond, keeping this carbon atom in front and just rotating our substituents. Okay, let's talk a little bit about 120-degree bond rotation and tilting substituents. So in this case, in terms of bond rotation, any bond can be rotated 120 degrees, rotating all substituents 120 degrees. For example, we can rotate the bottom. We can rotate this carbon-nitrogen bond, and that rotates our bottom substituents 120 degrees. To prove this, let's use a model and demonstrate that this in fact does work as intended. So let's make a model of this initial compound, and then let's go about showcasing this bond rotation. Okay, so here is the model of this compound. Now what I'm going to do is I'm going to take my bottom substituents and I'm going to rotate them 120 degrees. So for example, I can rotate them 120 degrees in this direction. That gives me now the chlorine pointing towards us, the hydrogen on the left in the back, and the iodine on the right, which directly matches the structure that we've obtained. You can do the same thing via swapping substituents, but if you have a model, you can just rotate your molecule however which way you want. Now, because we're often aiming to get the lowest priority substituent, which is often hydrogen in the back, this is often equivalent to looking down the carbon-hydrogen or the lowest priority substituent carbon-attached bond. To show what's happening here, if I want to place the hydrogen in the back, I just find the carbon-hydrogen bond and look down it. As we can see in this Newman-like view, the chlorine's on the left, iodine's on the right, the amines up top. Let's try to take the following molecule and rotate it so that the hydrogen is in the back. You can do this with a model kit, and in fact, I would encourage you to make a model of this compound. So here's a model of this compound. Bromine up top, alcohol in the back, methyl group on the left pointing towards us, hydrogen in the plane of the page. Now what we're going to do is we're going to rotate this molecule. So we're looking down the carbon-hydrogen bond, hydrogen's in the back, and now we draw what we see. The bromine up top, methyl group on the right, alcohol on the left. Let me check. Sorry, the alcohol shouldn't be there. The methyl group is on the right. And the alcohol is on the left. This is really important, this idea where you can take a model, place the lowest priority substituent in the back, and assign the configuration. Using this skill that we learned from drawing Newman projections can let you quickly do that. Again, you're just looking down the carbon atom and looking down the bond between the carbon atom and the lowest priority substituent, which is hydrogen. Okay, let's look at another example. Let's talk a little bit about molecular tilt now. In this case, if you're tilting the skeleton, you readjust the lines while keeping the dash wedge notation the same. Let's showcase this example of molecular tilt using a model kit. So let's get the sulfur group, the methyl group, the amine and hydrogen all connected and ready to go. Okay, so here's our initial model. The amines up top, sulfur's on the right, methyl's pointing towards us, the hydrogen's pointing away from us. So if we take this bond and tilt it 90 degrees, we now have the sulfur on the left, the amine on the right, the methyl pointing towards us, and the hydrogen in the back. Let's keep going now, and let's tilt once again, another 90 degrees. Now we have the sulfur up top, the amine on the left, the methyl pointing towards us, the hydrogen pointing away from us. One last tilt 90 degrees gives the amine on the left, sulfur on the right, and the methyl group in front, and the hydrogen in the back. So there are many ways that you can twist and rotate, tilt and rotate the skeleton. Just to show it once again, we tilt once again, and we tilt once again. Many ways to draw the exact same molecule. So let's do some practice and let's assign the configuration at each stereocenter. I would encourage you to make a model of each of these compounds, as it can be a very useful tool to assign the configuration at each stereocenter. So take a few moments, work through this example, and then we'll discuss these two examples momentarily. Okay, so here is the model for this first compound. Initially, we have the hydrogen on the left, the methoxy group on the right, methyl in front, fluorine in the back. So what we're going to do is we're going to rotate this structure so that the hydrogen is in the back. In this case, now what we have to do is we just have to draw what we see. So in this case, we have the carbon. The methyl group is pointing up top. The hydrogen is in the back. And we have the methoxy group on the left, the fluorine on the right. In terms of priority, it goes fluorine, oxygen, carbon, tracing from highest to lowest priority. This in turn gives us an R stereocenter. So again, just to show this rotation, here's our initial state. We rotate it so the hydrogen's in the back. And from here, we trace from highest to lowest priority. That moves clockwise, and thus this is an R stereocenter. Let's do the next example now. So this time, let's make a model. Again, because this is a model kit based bonus lecture, we're going to be using our model kits a fair amount. Again, given you can use model kits on exams, it's a pretty useful tool to get familiar with. Okay, so we're almost done putting together a model using our model kit. So let's share the camera. So here's what our initial model looks like. The hydroxylamine groups on the right, amines up top, methyl group. Let me just adjust this view. Here we go. So the hydrogen is pointing towards us. The methyl group is pointing away from us. The amine is pointing up. The hydroxylamine group is on the right. Now what we're going to do is we're going to rotate this molecule so that the lowest priority group, which is hydrogen, is in the back. And now we're just going to draw what we see. So the nitrogen's up top, the methyl group's on the right, hydroxylamine's on the left. Just to check, as you can see, everything matches. From here now, we can assign priority. The hydroxylamine group's priority 1, amines priority 2, methyls priority 3. Tracing, this gives us an R stereocenter. So this is why you need to be familiar with molecular rotation. Oftentimes you have to redraw or rotate your molecule so the lowest priority substituent is in the back. Let's talk about another example of molecular rotation. And this example covers the horizontal and vertical flip. To this end, let's make a model and then we'll discuss. Okay, so here's a model. I've made the boron yellow just for visual clarity. So as we can see, we have the boron on the left, the chlorine in back, the alcohol up front, and the amine on the right. As we can see, everything matches up. For a horizontal flip, all we do is we invert our molecular skeleton and invert the dash wedge notation. So as you can see, now the amines on the left, borons on the right, and now the chlorines in front with a wedge instead of a dash, the alcohols in the back with a dash instead of a wedge. So again, here is our original. We rotate it horizontally 180 degrees. You see the skeleton flips and the dash wedge configuration flips. This is really the exact same operation as looking at your molecule from the front versus the back. So let's showcase that. So here is our initial front view. So here is except instead of boron, we have hydrogen. So let's make this model. So here's our front view. So this is looking at the molecule from the front. Here's the view of the molecule from the back. Front, back. As you can see, we flip our skeleton and the dash wedge notation at our stereocenter gets flipped. Initially, we have the amine with a wedge in front, the hydrogen in the back. Post flip, our skeleton gets flipped. The hydrogen is now in the front with a wedge, the amines in the back with a dash. Okay, so the second case concerns the vertical flip. So in the vertical flip, we invert our molecule vertically, and then we invert our dash wedge notation. So here's our initial molecular view. As we can see, the boron is on the left, amines on the right, chlorine is wedged in front, alcohol is dashed in the back. If we want to flip our skeleton vertically, we invert the skeleton vertically and we invert the dash wedge notation. So as you can see, the skeleton now has a different arrangement. Here's where we started, here's where we finished, and the alcohol is now wedged instead of dashed, and the chlorine is now dashed instead of wedged. Here's the before, here's the after image. Here's the before, here's the after image. Okay, so why is this important? It allows us to rotate our molecule to assign R and S configurations. So in this case, you're asked to assign the configuration at each stereocenter for the following molecules, and you may need to redraw the molecule as needed. In this first case, we have it already set up with the hydrogen in the back, so we have an S stereocenter. Let's try to tackle this second case. So take a few moments, make a model of this compound, and try to assign the configuration by rotating your molecule to place the lowest priority substituent, which is often hydrogen, in the back. So pause the video, work through this example, and then we'll discuss. Okay, so here we go here. So now we have the iodine on the right, chlorine on the left, hydrogen in front, alcohols in the back. So we have this all set up. Now we're going to rotate it so that the hydrogen is in the back. That gives us the following view. So now let's draw what we see. That gives us the iodine on the left, the chlorine on the right, the alcohol in front, and the hydrogen in the back. From here, we can assign priority. Iodine's priority 1, chlorine's priority 2, the alcohol's priority 3. Tracing, this gives us an R stereocenter. As a correction, this first stereocenter, as it's also clockwise, is also R. So in this case, both of these stereocenters should be R. In this case, the way that we got that was after rotation. Initially, the hydrogen's not in the back. We rotate our molecule so the lowest priority substituent's in the back. Tracing from highest to lowest priority, we have a clockwise rotation, which gives us an R stereocenter. So here's the clockwise rotation specified, going from priority 1, 2 to 3. Okay, let's keep going now. And let's talk about another aspect of assigning configuration, which is assigning the configuration to Fisher projections. So in this case, you have a choice to view your molecule from the left or the right-hand side. So let's make a model and then we'll discuss. So let's make a model of this structure and then let's show how we can view our structure from the left-hand and right-hand side respectively. So take a few moments, put together a model, and then we'll discuss. Again, I'm giving time as part of these lecture series for you to have enough time to make a model of each of these structures that we're looking at. Okay, so here we go. Here is the model of this compound. As we can see, we have the aldehyde in the back. We have the hydrogen on the right. We have the chlorine on the left. On the second carbon, we have the iodine on the right, hydrogen on the left, and the alkyl bromides in the back. Now, what we can do is we can view the molecule from either the left or the right. So in this case, let's see what happens if we view this molecule from the left. So I'm going to view it from this side. So I'm going to view the molecule from this side. As we can see, the aldehyde ends up on the left, the alkyl halide ends up on the right, and in this case, the chlorine is wedged, and we should also have the hydrogen with the wedge, and the iodine gets the dash. As we can see from our model, and that matches the lecture view. Okay, let's see the other perspective. So in this case, we have the following view. Let's look at it from the right. So looking at it from the right, we have the aldehyde on the right, the alkyl bromide on the left. This time, the iodine is wedged, and the hydrogen is dashed. Additionally, the hydrogen is wedged, and the chlorine is dashed. So as you can see, you can convert Fisher projections into dash wedge depictions by choosing and rotating your model to look at it from the left or from the right. Both views are valid. The reason why we may need to employ both views is each view may place the lowest priority substituent in the back. For example, in this case, in terms of priority, the priority ranking of groups looks like this. Hydrogen's in the back, so this first stereocenter would be R. To tackle the second stereocenter, we need to have the hydrogen in the back, the iodine's priority 1, the alkyl bromide's priority 2, the alkyl chloride's priority 3. This is counterclockwise, so the second center is S. So this gives us the configuration of R followed by S. So as you can see, why do we need to consider both views? Because sometimes both views are necessary. Another method that you can use is what's known as the cyclic method. So Fisher projections are derived and used for sugars. And as such, you can draw and contort your model so that your structure is in a pseudo-cyclic form, and that makes it easier to assign configuration, as cyclic structures are generally easier to handle. So let's make a model of this compound and let's show how the cyclic method works in practice. Okay, so here is the Fisher projection structure. Here's our model for this Fisher projection. As we can see, the aldehyde's in the back, the alcohol on the front carbons on the left, hydrogen on the front carbons on the right. On the second carbon, the hydrogen's on the left, alcohol's on the right, alkyl halide's in the back. So now what we're going to do is we're essentially going to draw it in like a pseudo-cyclic form. So we can almost treat it almost like it's a 5-membered ring. As we can see in this view, this oxygen here is wedged, it's pointing towards us, while this oxygen here is dashed, it's pointing away from us. So we can draw it in the quote-unquote pseudo-cyclic form. As we can see here, and we can also draw it the cyclic form rotated like so. In which case, the hydrogen is now wedged, as we can see, and the second carbon oxygen atom, this alcohol, is now also wedged. As we can see from this model view. Why is this useful? It gives us a Pretty quick and efficient way to assign configuration because we have two views where the hydrogen's in the back. So in this case, priority 1, 2, 3. This in turn gives us a S stereocenter on our first position. On the second carbon, we need the hydrogen in the back, which occurs in this view. Here we have priority group 1, the alkyl bromides, higher priority than a carbon attached to oxygen because bromine has a larger atomic mass. Tracing, this in turn also gives us an S stereocenter. So as you can see, the cyclic method can be quite quick in terms of assigning the configuration at stereocenters for Fisher projections. Let's take a look at another method now, and let's talk about assigning configurations for Newman projections and rings. In this case, you convert the Newman projection to a dash wedge structure, and you place the lowest priority substituent in the back, and then assign configuration at each stereocenter. So let's take a look at this leftmost compound. Let's in turn make a model that matches that Newman projection. And once you make the model, then we'll be able to discuss. So take a few moments, put together a model for this compound on the left, and then we will discuss momentarily. Okay, so here is our Newman projection view. As we can see, the methyl's up top on the front carbon, bromine's on the right, hydrogen's on the left. On the back carbon, we have the hydrogen on the right, the methyl group is on the left, chlorine's pointing down. So what we're going to do is we're going to rotate this molecule. In this case, we have the hydrogen in the back. So we're going to draw what we see in terms of this dash wedge depiction. Before I do that, I'm also going to rotate my back carbon so that that back hydrogen is also in the back. So now I have a view which places both hydrogen atoms in the back. And now we just can draw what we see. So in this case, in terms of the wedged group, we have the methyl group wedged. The bromine atom is flat. On the right, the chlorine atom is wedged, hydrogen is dashed, and the methyl group is flat. Okay, now from here we can assign priority. Priority 1, 2, 3, tracing, that gives us an S stereocenter. For the second atom, priority 1, 2, 3, tracing, this gives us another S stereocenter. Let's, again, just to show the process, you start with your Newman projection view. Now what you do is you rotate your molecule, and then you rotate your bond so that both hydrogens are placed in the back, as we can see from this view. Okay, let's now work on this next example. So in this case, the hydrogens are already in the back. So let's just make a model to see what we can see. So here is a model of this compound. As we can see, the methyl group and iodine are on the right. The hydroxyl group and the methyl group on the back are pointing up. The hydrogens are in the back. Here we rotate. We already have our lowest priority substituent in the back. So let's just draw what we see. The methyl group and the iodine are wedged. So looking at this carbon, we have priority 1, 2, 3. This gives us an R stereocenter. At our second carbon, priority 1, 2, 3. This gives us an R stereocenter. So in this case, both of the stereocenters are R and R. So as you can see, we were able to draw out and assign the configuration for a range of Newman projections. So this concludes this supplemental lecture focusing on molecular rotation and assigning the configuration at carbon stereocenters.